it's a joint work with Danny Willems. And the title is Anemone and Jive, Anemone and Jive, a new arithmetization-oriented tools for Plonk-based.
That in the title, this is precise for Plonk-based application to highlight the performance that we have in Plonk, but we also have very nice results in other metrics, as we'll see later. So this is a joint work with Pierre, Piros, Leo, Robin, and Veslin. Also, I'd like to say that I'm from Symmetric Crypto, and I know that in the room there are many zero-knowledge proof specialists, and I do not pretend to explain better than you how it works at the protocol level. So I'll start by giving my point of view, which is closer to a symmetric cryptographer. And before going into the main topic, I would like to give you a kind of motivation to explain the main idea of the presentation. So the objective is to show how we came to this. I mean, up to 50% of improvements in terms of Planck constraint of a highly optimized Poseidon. And then we can reach 51 constraints instead of 110, so this is very nice. And for the moment, Anemoi is the state of the art for Planck. So to reach this, the presentation will begin as follows. So first I'll present the background, the various emerging uses for us in symmetric crypto, and I'll also give a short definition of the C-set equivalence, which is really the main idea of our approach. And then we'll talk about Anemoi, Jive, and Danny will give the benchmarks. So in recent years, there have been a new trend to design a symmetric primitive for advanced protocols. So the idea is very simple. You have zero-knowledge protocols that need some symmetric primitive to be efficient. So depending on your needs, you will ask for specific primitives. And now, if we see that from our point of view, we have zero-knowledge protocols that give us the rules and the constraints that we need to respect to design a good primitive. So we have all the tools that are related to symmetric crypto, I mean, how to design a primitive, our securities, and so on. But actually, it's more complicated than this, because what we need are arithmetization-oriented primitives. So this means that classical algorithms are inappropriate in that context. And the important question is, what differs from the usual case? I mean, this is really important to answer that question to understand the challenges that we face as designers. So first thing is that usually in symmetric crypto, what is interesting for us is to work in very small field, f2 to the n, where n is like 4, 8. So for example, for the AS, n is equal to 8. And now we need to work in very large field, fq, where q is either a big prime number or big power of 2. So for example, we can work in fp with such a p. So we can really feel here that this is very different to work in fp with such a p than working in f2 to the n with very small n. So this also means that the operations are not based on logical gates or CPU instruction, but now we need to work with large fan-of arithmetic. And we also have new properties, because usually what is interesting for us is to have an efficient evaluation for implementation in software and hardware. And now what we want is an efficient verification for integration within advanced protocols. So really what is important in this slide is that we work in large field, and what is interesting is the verification. I mean, you probably already know this, but this is really important to insist on this, because this is really different from what we're used to. So we really need to think about other strategies to design the primitive. And more particularly, these protocols have highlighted the need to minimize the number of multiplication performed by the primitive in large Fano fields. So this means that we need to design function such that the verification uses few multiplication. So first approach is to say, okay, let's take a function so that the evaluation also uses few multiplication. So the idea is quite simple. You use a function e of low degree to perform the evaluation. This is not too expensive. And you use the same function to perform the verification. So this is not too expensive. But we might want to avoid this kind of construction because we might be vulnerable to some attacks. So this is how we came with the notion of CCZ equivalence. And our approach is the following. We say that a function is arithmetization-oriented if it is CCZ equivalent to a function that can be verified efficiently. So to put it simply, we take a function of high degree to perform the evaluation so that we have a high security level, and we'll take a function of low degree to perform the verification so that we have good performances. So maybe I just need to give a definition of this CCZ equivalence. Now, I can't talk about Anemoi without talking about CCZ equivalent. So we say that function f and g from fq to fq are CCZ equivalents if there exists an affine permutation that allows us to go from the graph of the function f to the graph of the function g after applying this affine permutation. So maybe this is very abstract definition. So let's see what is important to remember. The first thing is that verification is the same. I mean, if, for example, you want to check that y is the output of x using the function f, you can just check that v is indeed the output of u using the function g. This is the same. And we also have that the degree is not preserved. I mean, you can have the function f of high degree, the function g of low degree, and both can be CCZ equivalents. But what I really wanted to point here is that verification is the same, because again, we're in that context where we want to have an efficient verification. So now that we have defined CCZ equivalence, let's talk about Anemoi. And maybe before going into the details, I'd like to say why we've chosen Anemoi. I mean, when designing a primitive, an important part of the work is choosing the name of the primitive, actually. So our Anemoi is a family of ZK-friendly hash function, and the real Anemoi are Greek god of winds. So why? Because in our Anemoi, we have a structure that is highly inspired by a butterfly structure, and you know that a butterfly flies in the air. And so this is first explanation, and also you know that the wind can go in different direction, and in the team we're from different parts of the world. So this is another one. And maybe a last one could be that you can see that Anemoi begin with an A, and this is not too overused, so this means that when you Google it, we can appear on the top level, so this is quite nice. So let's come back to more concrete stuff. The main component of Anemoi is the fly cell. So this is inspired by a butterfly structure and a phase cell network. So if you're not very familiar with that notion, this is not really important. We're just going to describe the different operations that we need. So we need three functions, two quadratic functions and a permutation. And then we have two variants, the open fly cell and the closed fly cell. For the closed fly cell, we have two elements as input, two elements as outputs, and we use the two quadratic function and the inverse of the permutation. So the open fly cell is a high degree permutation. Then the closed fly cell also uses the two quadratic function, but this time this is the permutation. So this is a low degree function. Maybe let's take some examples. So in FP, we can use the square as a quadratic function. And for the permutation, we'll use x to alpha. And alpha is supposed to be co-prime with p minus 1, so that we have a permutation. And usually we take 3 or 5 because we want to have a small exponent so that we can have a few multiplication. So for the closed fly cell, we use the squares and x to alpha. And for the open fly cell, we use the inverse of alpha. So again, let's take some examples. So if we use this curve, we can use alpha is equal to 5. And the inverse of alpha is this one. So we can really feel here that if we use the closed fly cell, we have squares and x to the 5. So this is a low degree function. But if we use the open fly cell as we use the inverse of alpha, this will be a high degree permutation. And an important remark is that both variants are CCZ equivalent because there exists an affine permutation that allows us to go from the graph of the open fly cell to the graph of the closed fly cell. And what is the advantage of having the CCZ equivalence here is that we can have a high degree evaluation. I mean, if we use the open fly cell as we have the inverse of the permutation, and as we have seen before, this is of high degree. And we can have at the same time a low degree verification. Because here, if we perform the verification for the open fly cell, it will be quite expensive. So instead of checking that UV is the output of XY using the open fly cell, we'll prefer to check that XU is the output of YV using the closed fly cell, because this is less expensive. And we can do this because there is CCZ equivalence and verification is the same. So really, the advantage here is that on one side we can have high degree evaluation, so high security level, and on the other side, low degree verification, so good performances. So then we can use the fly cell as an S-box in the SPN construction. Again, if you're not very familiar with that notion, we're just going to describe the different operation. So basically, we represent the internal state of Anemoi as a matrix with L columns and 2 rows. So why having 2 rows? This is because we'll apply the S-box in columns, and the S-box is the fly cell, and you know that for the fly cell we have 2 elements as input, 2 elements as output, so this is why we can apply this in columns. And maybe I should say so that you can see that for each 2 branches, we have only 1 S-box. So this means that we have only one computation one exponentiation to the inverse of alpha, so we can save some computation by having only 1 S-box for 2 branches. And then we have what we call a diffusion layer, so this is basically a matrix multiplication. So we have a matrix multiplication for the first row and another one for the second row that basically correspond to the first one after applying a permutation. And finally, we have the constant addition where we just add a vector C to the vector X and a vector D to the vector Y. So we can also represent it like this. So we have our vector X, our vector Y, we add our constants, then we do the matrix multiplication, and then we apply our S-box. And this represents 1 run for the Anemoi permutation. And we will repeat this a certain number of times. And this is given by this formula. So it depends on alpha, the exponent, also on the number of branches. And this is to prevent some algebraic attacks. So if you want to use Anemoi, you can use this formula to compute the number of runs that you need. And then we'll use Anemoi for a different application. The first one is for a hash function for a random oracle. And in that case, what we have is an input of arbitrary length and an output of fixed length. So the idea is to use a classical sponge construction. So in that case, we add our message, and each time that we add a message, we apply the Anemoi permutation. So this is absorption phase. And then for the output, each time that we give an output, we again apply the Anemoi permutation. So this is the squeezing phase. So this is classical sponge construction. And for the something happening here, I don't know. There is a problem. No. This one, yeah. Sorry. And we also need Anemoi for a compression function for Merkle trees. So first, let's take the example of 2-to-1 compression function. So usually what was done in other primitive was to use a classical sponge construction, but we have some useless elements. So this is why we propose Jive. And in that case, we have our 2 elements, we apply a permutation, and we get 2 elements as output, and we basically just sum all those elements. So Jive corresponds to this. So we have our 2 elements as input, and we get 1 element as output. This is the sum of all of this. So this is 2-to-1 compression function, and we can also generalize this with B branches. So again, we have our B branches, we apply a permutation, we get our B branches as output, we sum all those elements. This is Jive B, and from B elements, we get only 1. And now I'll let Danny explaining about the benchmarks.
So, thanks, Clémence. So, as Clémence said, we will now talk about performances in different arithmetization, but also in CPU, and especially in Plonk, because we get an interesting result that halves the cost of constraints compared to the state-of-the-art implementation that we did at Nomadic Labs, which is the Poseidon. So we're gonna, yeah, of course, yeah. So we're gonna first start by, we decided to compare to 3 other primitives, so Rescue Prime, Poseidon, and also Griffin. And we're gonna start first by describing the different, the other primitives. So let's start with Rescue Prime. So Rescue Prime is a traditional SPN structure where each round consists of 2 different S-box, one low degree and one high degree exponentiation. For Poseidon, it consists of what we call full rounds and partial rounds. So full rounds operates, the S-box operates on each element of the states, and partial rounds operates on only one element of the states. And because of these partial rounds, we need to have a high number of rounds, and it's going to have an important cost in terms of Plonk, as we're going to see later. And for Griffin, which is quite recent, it's also an SPN structure. But the S-box is quite a new design, so it consists of one high exponentiation on the first element of the state, and after that it's only low degree exponentiation. So we summarize the constraint cost in this table. So you can see that most of the time Anemoi is ahead from the others, and for R1C, as you can see that we've got a lower gap between Anemoi and the other primitives, and it's because the linear layer for the additions for the linear layer come for free. But for Plonk, we can see that as the addition has a cost, the linear has a cost quadratic in terms of the state size. So as I said, for Poseidon, we have a high number of constraints, and for Rescue Prime also. And if we focus only on Plonk, we can see that we've got very nice performances. We always have better performance than the other. But we can even go lower if we use additional custom gates, as traditionally used in Plonk, like the custom gate for the low degree exponentiation to alpha, and also the next wires. So we can get down to 79 constraints compared to the state-of-the-art 110. But we can also go lower by adding another custom gate, so the quadratic custom gate that has a negligible overhead on the prover and verifier time. Regarding the native performances, for Poseidon, we only need to perform low degree exponentiation. So low degree exponentiation has cost 100 times less than the high degree exponentiation. So it's for this reason that for Poseidon we have a relatively small CPU time compared to the other. For Rescue Prime, we've got to operate on each element of the state. We've got to make a high degree exponentiation on each element of the state. So we've got this time. For Anemoi, it's only on half, and on Griffin, it's only on one element of the state per round. So to conclude, what we did is we introduced a new family of ZK-friendly hash functions, so that we call Anemoi, which is efficient across different proof systems, especially for Plonk. But also we made new observation of fundamental interest. So for instance, the standard components that we call flystall and Jive that can be used for other constructions. And also we identify a link between arithmetization-oriented and CCZ equivalence. So to summarize, we started from strong mathematical foundations, which is CCZ equivalence, that gave us good security level, but also good performances. So you can find more details on ePrint. The paper is there, and also there have been other works that improve Anemoi for different cases that you can also find there. So thanks for your attention, and if you have any question, feel free.
Thank you. Questions?
I wanted to know what are the advantages of using Jive and if it was possible to replace it by other mode of compression such as Davis-Meyers or Miyaguchi-Pernil.
Okay, so I don't know about this design, if they can be applied in that situation. I don't know.
We can go offline.
Yeah.
Other questions? Okay, thanks again.